Okay, so for question 3, our approach is to go through each of the sorting algorithm, and at each algorithm, we will provide a very brief outline of what does the algorithm do, and then we will go into runtime analysis, and then we will also discuss the relevant sub-questions of question 3 that pertains to the particular algorithm. Okay, so first up, we have selection sort. For selection sort, it like for all of the indexes of the entire array, at each index, we iterate through the rest of the array to find the smallest item, and then we perform a swap between the smallest item and the item at the current index, and we increment our index and repeat the same procedure again. So for example, if we have an input array of 8, 1, 2, 17, and 5, we will start at index 0, that is 8, and the smallest item would be 1. So we perform a swap between 8 and 1. And at index 1, the smallest item is 2. So we perform a swap between 8 and 2. And we repeat a similar procedure until we have reached the end of the entire array. So let's consider the best case. We will kind of assume that the best case is when we have a sorted array, right? But let's see what happens when the array is sorted. That is, our algorithm doesn't actually check for whether an array is already sorted. So it will still look through the entire array to get the smallest. So in this case, the best case is kind of similar to the worst case. That is, we still have to perform the iteration and the loops. That is, the number of items we have to iterate over to get the smallest item is to the order of n, and there are n loops in total because our array is of length n. So the runtime would be of theta n squared on average. Okay, so next up, we have insertion sort. For insertion sort, we also iterate through the entire array. We start at index 1, and at each subsequent index, we swap the item leftwards until the next left item is actually smaller or equal than our current item. So for example, if we have an input array, the similar input array of 8, 1, 2, 17, 5, and we start at index 1, which is 1, 8 is larger than 1. So we perform a swap and we increment our index. So now at index 2, we have number 2. 8 is larger than 2, so we perform a swap, but 1 is smaller than 2, so we stop. When we are at index 3, that is 17, no swap is needed because 8 is smaller than 17. But when we comes to 5, as you can see, there are 3 comparison checks and 2 swaps done. And so we get to the point that 2 is smaller than 5, and we end our algorithm. So the best case would be that when we have a sorted array, like for example, 1, 2, 3, 4, to emphasize sorted array in the order that we want, which in this case is ascending. So we have to iterate through n items just once. So our runtime would be theta n on average. But for the worst case, we would have an array that is fully sorted but to the opposing direction. Like for example, we need an ascending order, but we were given a descending order sorted array that is like 4, 3, 2, 1. We have to iterate through n items, and for each item, we have to swap to the very left, that is to index 0. So the number of swaps performed for a single item would be to the order of n. So in this case, for the worst case, it would run on theta n squared. For question 3.1, we were asked to give 2 examples of array for both best and worst case. So the answers are being provided here and they are being highlighted in blue. For 3.2, for example, if you are given a reverse list, each of selection sort or insertion sort is better. If we pick a criteria that is the number of swaps performed, let's see what would happen. For selection sort, we know that we only need to perform a single swap between the smallest item and the item at the current index. So in total, we are iterate through the entire array, which is of length n. In total, we would only have to perform n swaps. However, for insertion sort, as explained earlier, like in the worst case, we always have to move an item towards the leftmost position, which is index 0. So in total, there would be a big O and square swaps performed. So if you are choosing the criteria of number of swaps, that means that selection sort appears to be a better choice. All right, the third algorithm that we have is merge sort. So that is, given an array, we recursively divide the array into halves until we get to the base case that is for each half, we only have one item in it. So, and then we start merge sorting them until we get two halves with length n over 2. And then we perform our final call of merge sort to get the final sorted array. So given the same input array of like 8, 1, 2, 17, and 5, the final two sorted halves would be 1, 2, 8, and 5, 17. And then we would have like 3 pointers with 2 on the sorted halves, and the third one would be pointing to the output array. And we will compare item by item across the 2 sorted halves, and then we will add the smaller item at each comparison to the output array, as shown here. So for runtime analysis, for both best and worst cases, we know that recursion to divide the array into halves would create a tree of height log n. And at each level, we do n operations of comparison and merge. So the runtime would be theta n times log n. Okay, for heap sort, we are essentially using the properties of heap to help us with sorting. Specifically, we would using a max heap that allows us to remove the largest item, that is the root, and then we can just swap the removed root with the rightmost item of a heap, and then gradually build our output array. This explains part 3.3. Since we're talking about algorithm, to see how it actually works, let's jump into 3.4. For 3.4, we are given this array 3 to 1, 5, 6, 8, 7 by the protocols of array representation of a heap. It will be translated into a tree as shown on the right. As we can see here, it doesn't really follow the properties of a max heap. That is, the parent node is not of higher values than the children node. So we have to heapify the array. As we can see here on the left subtree, 6 is the largest value, so 6 should be pushed to become the parent. On the right subtree, 8 is the largest value, so 8 should be pushed to become the parent of the right subtree. And among 3, 6, and 8, 8 is the largest value, so 8 should become the new root. But at this point, 3 is less than 7, so 7 should be pushed up to become the parent of the right subtree. And at this point, we would already achieve the structure of a max heap, and it can be represented as this following array that is highlighted in blue. So now we can perform heap sort. That is, we remove the root and then we swap it with the rightmost item of the heap, that is 3. Which will leave us with this structure over here. As we can see, the heap order is again violated, so we have to arrange it to get 7 as a new node, 7 as a new root, and then we remove 7, we swap it with the rightmost item, that is 1, and we would end up here. Again, rearrange the heap to get 6 as our new root. Remove 6, swap it with the rightmost item 2. It would get us here. And we would have to rearrange it again to get 5 as the new root. And then remove 5, swap it with 1. It would get us here. And rearrange the heap with 3 as the new root. Remove 3, swap it with rightmost item 1. And then rearrange the heap to get 2 as the new root. Remove 2, swap it with the rightmost item 1. It would get us the final sorted output array. So our job is done. Okay, so for the runtime analysis, we need to know that building a heap with bubbling operations, that is like for a general array, it would take us n times log n time. For the remove operations with the bubbling and sinking, it would take log n time too. However, if all elements are equal, there will be no bubbling and sinking operations needed at all. So when we are building a heap or when we are removing the root, it would only take n time. So in the best case, that is, we have all items that are equal to each other. Heap building and remove operations, it would take on average together and runtime. For the worst case, that we have a general array, heap building and the remove operation would take on average of n times log n runtime. Okay, the final sorting algorithm we have is quicksort. We first decided on some pivot taking strategy, and once our pivot is chosen, we would divide the array into 3 groups. First with elements that are smaller than the pivot, and then with elements larger than the pivot or equal to the pivot, and then we recursively sort the first 2 groups. Again, since we are talking about the algorithm, let's jump into 3.5 to see how it actually works. Okay, so for 3.5, we are given an array of like 1, 3, 8, 2, 6, 4, 5, 9. And in this question, we are asked to pick the middle element as the pivot. And if there is no exact middle, we will pick the element to the right of the middle. We are given an array of length 8, and 8 divided by 2 will give us 4. Since index 4 is not the exact middle, we will increment it by 1 to get to the right. That is index 5, which gives us item number 6. Okay, as we can see here, that it is not well sorted into the 3 groups that we need. Specifically, 4 and 5 should be on the left side of 6 since they are smaller than 6, and 8 should be on the right side of 6. So we have to sort it into this representation here. Yeah, as we can see, we now have all the items smaller than 6 at the left and items larger than 6 at the right. And we would further recursively sort these 2 subparts. But notice that on the right side, it is already sorted. So you would just leave it as it is. But on the left side, 2 would be chosen as the new pivot since it is the exact middle of index 0 to 4. So yeah, when the pivot 2 is being chosen, we would again perform our sorting into the 3 groups. There is no items equal to 2, so only 1 should be at the left of 2 and 3, 4, 5 should be at the right of 2. So once that's done, we would have this particular array over here, and we would again recursively perform quicksort on the subpart or the section 3, 4, 5, where 4 will be chosen as the new pivot since it is the exact middle. But once 4 is chosen as a new pivot, we can see that like 3 less than 4 is at its right and 5 larger than 4 is at its right. with 3 less than 4 is at its left and 5 larger than 4 is at its right. So it's already well sorted. And yeah, so at this point, the algorithm ends because we already have our final sorted array. Okay, so back to runtime, we can notice that the runtime for quicksort actually depends on the number of partitions. Each in turn depends on the position of our pivot. So in the best case would be that the pivot position is always at the middle every time. So in this case, our operation would be quite similar to building a tree of height log n with n operations at each level. Hence, the runtime would be theta n log n. In the worst case, our pivot position will be at the start, that is index 0 every time. So we have to iterate through array length of n for n times. So the runtime would be theta n squared. And that's it for question 2. Thank you.